I have been thinking a lot about the Collatz conjecture recently. It is such an interesting question due to its simplicity. It gets even more interesting as you try to solve the problem. I've decided to do a short series on the subject. I want to explain what I've learned from studying the structure it produces. In this first part, I will just begin outlining the logic that I base my point of view from. The question asks, if you take any starting number and apply the rule that it must be halved if possible, otherwise it must be multiplied by 3 before adding 1 to make it even, will the value always reach 1 regardless of the starting value? Another way to ask this question is if there are any values that will never reach 1, either by looping back to themselves infinitely or by always growing to infinite values. One major difference between this problem and many others is that there are 2 different rules being applied, based on divisibility by 2. This immediately makes the question a modular mathematics question. 0 mod 2 is divided by 2, essentially changing the factors of 2 into factors of 1, basically erasing them. On the other side, 1 mod 2 is multiplied by 3 and added to 1, which is always even after a single step. If you look at the way the modular sets evolve, as we look further into the problem, we will see several profound patterns within. The easiest of which is the ruler function. This is the comb of divisibility by 2. An even value will halve down to an odd value based on its position in the ruler function. As you count by 2, the amount of times you can divide the value by 2, known as the halving count, sometimes referred to as the k-value, follows a binary progression. First, half of all the values have a halving count of 1. This is 2, 6, 10, every 2 mod 4. To build each new step, it's fairly simple. The first member of each modular set is the first value with the next higher halving count, and the gap between members is double that. So 4 mod 8 has a halving count of 2. 8 mod 16 has a halving count of 3, and so on. Altogether, this produces the ruler function that looks like 1, 2, 1, 3, 1, 2, 1, 4, 1, 2, 1, 3, and so on. When you look at the ruler function, the first member of each new higher k-value set reaches 1. This is 2 with a k-value of 1, 4 with a k-value of 2, 8 with a k-value of 3, and all of these reach 1 because they are just powers of 2. The later members reach later odd values like 6 or 12 lead to 3, and 10 or 20 lead to 5. This becomes important for more than just the even numbers themselves, but also for the odd numbers who are tied to them in their sequences. Since the odd steps multiply the value by 3, a single halving step is insufficient to counteract the growth it causes. 2 halving steps are more effective than an odd step, so every value with a k-value of 2 or more will result in a value that is lower than it started with. If all values did reduce after the first halving step, the question would already be solved. However, the even numbers that have a k-value of only 1 cause the values in a sequence to grow. These growth values are the only cause for doubt in the system. Since the evens with a k-value of 1 account for half of all even numbers, then all the odd values that lead to these even numbers account for all half of odd values. This means that half of all odd steps result in growth. The point where growth happens are at powers of 2 minus 1. This is also to say that evens with a k-value of 1 minus 1 are odds that do not grow. Let's look at the evens with a single halving count minus 1. That's 2 minus 1 is 1, 6 minus 1 is 5, 10 minus 1 is 9, and so on. So every 1 mod 4 does not grow. With the same logic, the evens with a halving count of 2 minus 1, so 3 mod 8, all grow once to the next odd, but then the next odd will always be a 1 mod 4. And this continues with higher k-value evens minus 1, causing longer sprints of growing odd values in a sequence. An even value with a halving count of 6 minus 1 will be an odd that grows for the next 5 odds it reaches in its orbit. This is all based on powers of 2. At least it seems that way. That's where I'll stop for this video. Thank you for watching.